Hello, and welcome to Google Cloud AI Virtual Training. My name is Andrew Furlich, and I'm a staff member at Google Cloud AI Developer Relations. Today, we'll be discussing part 8 in our 10-part Junior Data Scientist series on data distribution. So let's get started. So, on our data distributions, this is our overview for today's talks, what we're going to cover. First, we're going to talk about the principles of data distributions and how they affect machine learning. And then we're going to talk about training for an out of distribution. And then finally, I'm going to walk you through a step-by-step example. So this whole we're talking about when distributions really relates to the model accuracy. And there are many techniques we utilize to try to increase the performance or the accuracy of our model. And for example, we may increase the training time. We might increase the depth or width of the model. We may add regularization. We may expand the data set with data augmentation, or we may increase hyperparameter tuning. While above may or may not improve accuracy, in the end, the limitation is ultimately the data set we use to train the model. And our goal here is that whatever model we want to train, we want it to generalize when it's deployed into the real world and it's making predictions on what it sees in the real world. Okay, so let's get into distributions because that's what really all this is about. So the field of statistics deals with algorithms that are not deterministic, meaning there isn't a linear relationship, x equals y, x plus 1 equal y plus 1, or a strong linear correlation between the inputs and the outputs. It's a non-linear relationship. And these algorithms, we call them models. And we call them models because they model the behavior, how to make an output and outcome prediction over some probability distribution. We don't say it's absolutely 1 or 0. We say it's 0.9%, 90% or 82.5%, etc. That's our probability distribution. Okay. And so we're going to dive deeper into distributions and how they affect the training of a model. So we'll talk about a population distribution, a subpopulation distribution, and a sampling distribution. So a population distribution, the easiest way to explain it is, let's say, for example, you wanted to predict the shoe size of an adult male in the United States. Well, then the population distribution of this model would be all the adult males in the United States. That is, if you had every single adult male in the United States, their shoe size and some characteristics, those are the features you're going to train on, then that distribution would be a population distribution. Okay. But the reality is that will never happen. Okay. So you're going to have some random samples, right? Okay. And each random sample has some randomly selected batches. And that one batch or random sample has some probability distribution of how representative it is of the population. Okay. So our goal when we can't get the entire population is to come up with a distribution we call a sampling distribution. So it's a collection of random samples and enough of them and distributed enough of them that makes sense. They model the population within some probability. Okay, we're going to call this a sampling distribution. Okay. And this kind of like, think about this, not just in the shoe size, but what you may be more familiar with, polling. You hear polling data all the time, okay? They say this candidate's polling X and this candidate's polling Y with an error of plus or minus, say, 3%. Where did that 3% come from? Okay. Well, it's this idea here is you build a sampling distribution, and using statistics, you can make an estimate of how likely it is representative of the population within some error. Okay. So a subpopulation distribution. Okay. And this was really important for you to understand. Regardless of how large and comprehensive your data set is, it's likely a sampling distribution of a subpopulation and not the population. And what do I mean by that? A subpopulation is a subset of the population that is defined by a set of characteristics which would not have the same probability distribution of the population. So let's take a simple example. Let's say you have a chain of stores that specialize in selling sports shoes to professional athletes, and that chain is across the entire United States. And you do a great job getting sufficient samples to develop a sampling distribution which is predictive of that subpopulation. Well, the problem is it's unlikely to be representative of the population of the whole, all adult males. Okay, so we have a difference here, right? So if we trained on this, we probably have a really good application for the subpopulation for professional athletes. But the problem is there that difference between that subpopulation and the remainder of the population is called the out of distribution. And can we generalize to that? And that's what we're going to uh, talk about here in the next part. So out of distribution. So I'm going to demonstrate the concept using the MINTS data set. So MINTS is a data set of 70,000 images. They're all handwritten, and they're proportionally balanced across each digit. So each digit has 7,000 images. And it's super easy to train to get near 100% accuracy on this data set. And hence why we call it the hello world of example of machine learning. But almost all in the wild applications of a trained model, a MINTS model, will fail because the distribution of images in MINTS is a subpopulation. Okay, so let's go a little deeper what we mean by that. So MINTS is also known as a curated data set. What is a curated data set? Well, that's when a data curated has selected samples for inclusions whose characteristics meet a definition. In this case, MINTS, each example is 28 by 28 with the digit centered in the middle. The digit is white and the background is gray, and there's a 4-pixel padding around it. So every curated data set model is a subpopulation. Okay, so now I'm going to walk you through an example where you can see how training a model on a subpopulation, what happens when we do prediction in the outer distribution area, and then what things could we try to get it to generalize to the out of distribution. So we'll start off with some housekeeping, setting up the environment. This is just a little code snippet if you wanted to repeat this on your own. We're just importing some TensorFlow Keras layer stuff to build our models. And we're going to import the MINTS dataset from TensorFlow Keras. Okay, and then we're going to go ahead and load it. And remember, when you load it, the data is not pre-processed, so all the pixel data is still that original integer data between 0 and 255, and the labels are still, a 1D vector. They're not, scalar. They're not one hot encoded. So first thing we got to do is do some of our data pre-processing, right? So a couple things we want to do. First, we want to normalize our pixel data. So we're just going to divide it by 255, right? And then convert it to our float 32. Okay, remember in NumPy, when it does floating point operations, it does it in float 64, double precision. So we want to lower it back down to float 32. The other thing in TensorFlow Keras, the models expect to take input as height times width times the number of channels. Okay, but the MINTS data set is actually height by width. There is no channel in it. So we need to reshape it to add a channel of 1. And that's what this reshape here does. Okay, so now our data is ready. If we were to actually print the shape, you would see an X-train. We have 60,000 images, and then the test 10,000, and they're 28 by 28 by 1. Okay, and correspondingly, the same thing here in the labels. Apologize that sometimes that gets covered up. And we're also going to set aside a copy of the train and test data in its original format. Okay, so here's our challenge. We're going to create 2 additional test data sets as an example of what the trained model may see in the wild. And these 2 additional data sets contain examples that are not represented by the training data. That is, there is no training data. They're not used in the training data, and hence we refer to them as the out of distribution. Okay, so the first one is our inverted, and you see the little code here. We're just going to make a copy of the test data, not the training data. You remember, it's seen the training data, it's never seen the test data. And we're going to go ahead and invert it. So that means all the gray digits now instead of being white digits on gray backgrounds, it's going to be gray digits on white backgrounds. And then we're going to make another one where we're going to shift all the images by 4 pixels. So remember, the original ones were centered. Now they're a little bit off-centered. And since there's at least a padding of 4 pixels in the curated data set, none of the digits will get clipped. So our X-test inverted and our X-test shift will be our out of distribution test data sets. Okay, and a quick look of what they would look like. So I took one example here of it's digit 7. Here's what it would look like in the inverted out of distribution, and here's what it looks like in the shifted out of distribution. So let's get started. So we're going to start off with a simple DNN. Practically any DNN will get you 97% or better accuracy. Okay. And I created a little function here, just a helper function to make us DNNs. Nodes here, it's just a list. Every element in the list represents a layer. So if there's 2 elements in the list, it's 2 layers, and the value is just the number of nodes on there. Okay, so here's our first test. So we're going to make a single layer, a DNN, 512 nodes, and we're going to train it for 10 epochs. It's not a lot. For a batch size of 32. But even with that, we immediately get really high accuracy. So on the training data, I got 99.6. Wow. Okay. Of course, what counts is the test data or the holdout data, but not too bad. It's really close. 97.9. That's almost 98%. This is a great model, right? Okay. So now let's evaluate it on our outer distributions, the inverted and the shift. Oh my gosh, totally 2% on the inverted, shifted 41. Well, that might be a much higher number, but that is way off. And even here on the inverted is kind of really odd, because if you think about it, if I made a random guess, there's 10 digits, right? I should have 10% accuracy. This isn't even as good as a random guess. This model totally cannot generalize to out of distribution. So what do we do? Well, let's go take some of our standard techniques. We could try making the model wider. So we'll increase the number of nodes on the input layer. More nodes, better learning, right? So now we make it 10, 24 nodes. We double them. Let's repeat it. Okay, essentially nothing changed. It's still in the 40% range for the shifted. This is just noise. Anything under 10% is clearly noise. It's not even as good as a random guess. So going wider did nothing. Let's try going deeper, right? Okay, so we do 2 layers, 512, 512. It's still essentially the same here, so in that 40% range. Okay, now it's at least as good as a random guess. Okay, but essentially going deeper didn't help us generalize into the outer distribution. So let's add some regularization. That's got to do it, right? So we'll just use dropout And the way we wrote that function is the first layer will start at 50% and every layer will cut it in half. We'll take that same 2-layer model we used. So the first layer is going to have 50% dropout, the next one 25% dropout, train it the same way. Now let's see what happens. Really, essentially, absolutely nothing happens. We're still in that 40% range for shifted. And again, we're back into that under random guessing noise for the inverted. Okay, probably time to stop trying to do it at DNN. Let's use the CNN. At least with a CNN, we know that it can learn spatial relationships. And perhaps the convolutional layers will also filter out the background and the whiteness of the data. So let's see what we get. So I trained this CNN on the curated minced data set, and then test evaluated on the test or holdout data for it and got 98%. So pretty good. Okay. Now that we have it trained, in that case, I actually trained it with this one that had a single layer. Uh, oh, let me repeat here because I think I skipped something here. I forgot to explain this little function here. Again, this is our helper function for making a CNN. Right? Filters is a list, so the number of elements is the number of convolutional layers, and the value of each element is the number of filters. So in our first one here, okay, I make a single convolutional layer with 16 filters. We train it on the test holdout data here. You can see where I got the 98%. And now let's try it on our out of distribution. Well, you can see there's been a significant increase. So roughly they're both in the 50-ish percent range. It's still not good enough, but you can see right off the bat, knowing spatial relationships, how effective that is as a first step in trying to recognize or predict things in the outer distribution. So it's a CNN. What's another way of trying to get more accuracy? Go deeper. So we'll add a second layer. So the first one's got 16, the second one's got 32 filters. We do it again. Yeah, we're really getting better. We're now 76% on the shifted and 63% on the inverted, but we're still way short of that 98% we got in the in distribution part. So let's try augmentation, okay? And this time I'm going to randomly shift my images up to 20%, okay? That's about 6 pixels, okay? But it'll be a random amount, 1 pixel, 2 pixels, 3 pixels, 4, so forth, okay? And we go ahead and train it with that, and we get even a little bit better accuracy on the test holdout data. We're now at 98.6, and now we tried in our inverted ones, and on the shifted one, we did great. We're practically the same. Just that little bit of augmentation trained it to recognize that out of distribution, even though it's never seen any of those examples from the inverted test data holdout set. Okay, but you can see it didn't help us in inverted. As a matter of fact, inverted just practically crashed. Okay. So without using really advanced pipeline techniques, which we haven't really talked about yet, and we will be subsequently talking about, really the next thing you could do is sort of look at that out of distribution. How can I expand my existing distribution to be more representative of it? So we're going to try to tackle that last one of the inverted, trying to get the model to filter out the background and whiteness of the digits. And what we're going to do is we're going to take 10% of our original training data, and we're going to invert it like we did with the test data. Now, the reason we're using the training data, not the test data, is we don't want to train with that inverted out of distribution. Okay, so we're going to use the training data, and we're going to invert 10% of it. And you ask yourself, why 10%? Well, in general, when we want to train a model to filter out something, we generally can do it with as little as 10% of the distribution of the entire training data. So here I take 10% of the copy of the original training data. Of course, we normalize it, we reshape it. corresponding labels, and then we're just going to append it to the end of our images and our labels. So now we have an expanded training data set. And so now I test it, or train it, excuse me, with the expanded data set. Okay. And what do we get here? Well, we get about the same accuracy. We shouldn't really expect it to get any more accuracy, because in the test data, there are no examples of the outer distribution. But now when we evaluate it on both our outer distributions, we're getting excellent results, about 96 and 98 here. So now at least we've trained this model to generalize to two out of distributions that are not part of the curated MINT data set. So as a final challenge in the West for myself, I took that last train model. Great model, isn't it? And I did a random search, random Google image search on handwritten digits. Okay. And then just grabbed a bunch at random. I observed some were colored. Some of them were drawn with a felt pen, another one with a paintbrush, another with a crayon drawing by a young child, etc. All randomly. And so I ran them through, evaluated, and I got 40% of accuracy with above trained CNN. So there's a lot of work to do to make models generalized to the out of distribution. So as one final thought I'm going to leave you with here is, presumed you developed a model for use in a factory to detect defects in parts. And you got this camera, it's in a fixed position or perspective pointing down at a conveyor belt, and the image, the parts are coming by, and you use those same images to train it. Okay. And it's a great model. It's just wonderful. But, it's an older factory, the conveyor belt, it's a gray conveyor belt, all these ridges on it. And, one day the owner just kind of feels it'd be nice to get a new conveyor belt, and one that has some color to sort of lighten up the factory. So he replaces with this brand new, nice, shiny, smooth yellow conveyor belt, and your model fails. What happened? Okay, well, thank you for watching. I hope you enjoyed this, and of course, stay tuned. We have 2 remaining parts for our Junior Data Scientist series. Both of them focus on the production pipeline. Part 9 covers the data pipeline part of it, and Part 10 will cover the training part. And then in July, we'll start our Intermediate Data Scientist series, and we'll start going to start talking about things we call like model fusion. We'll be talking about more advanced design patterns, the composable design patterns, and start sort of getting you introduced into automatic training. And in the fall, we'll be doing our Advanced Data Scientist series, where we'll really go full into model amalgamation, machine design, and the entire world of automatic learning. So look forward to our sessions, and I look forward to you watching. Thank you.